Hello everyone, this is Dr. Fu from Hofstra University. It is my great pleasure to present our recent work on how to produce an efficient zero-knowledge proof for regular language. This is a joint work with my students, Michael, Jillian, Jan, and Dia. To motivate the work, let's think about how an email exchange server provides user safety. A common practice is to simply run antivirus on incoming emails. But this approach usually comes at the price of user privacy, because every single byte of an email would be visible by the email server. So instead, the sender could actually encrypt the entire email so that the email server has no idea of what's behind the encryption. And then she could provide a zero-knowledge and short proof which certifies that the email behind the encryption is malware-free. In terms of that, it will pass the virus checkers. So we have many similar application scenarios in the context of secure communication. For instance, one could certify that an encrypted DNS request has no blocked websites. Or one could convince a router that encrypted packets would already pass the intrusion detection system, but without disclosing their contents. Since nowadays, most of the prevalent virus scanners and intrusion detection systems use regular language for specifying the policy sets or signature sets, we call this problem the zero-knowledge program for the regular language membership. More exactly, we have a prover who knows a secret input string and an encryption key. We have a verifier who knows a public finite state machine A that captures a good regular language. And the goal of the prover is to produce a zero-knowledge proof which asserts that this secret input string belongs or is accepted by this finite state machine. In theory, this is not a problem because we all know for a long time that all MP statements have a zero-knowledge proof. So if we use the prevalent Zkreg technique, we can simply encrypt the logic using arithmetic circuits, and we get a short proof. But the real challenge is the real-world problem size that we have to tackle. So take Climb AV as one example. Its hexadecimal signature set alone would generate a huge aholchoracic autometer with 19 million states and over 300 million transitions. This is a problem size which is much bigger than the prevalent zero-knowledge proof system that can handle. So in this work, we are taking a commit and a proof scheme. So basically, we are designing and implementing a hybrid prover system. So for the hash and encryption operations that we need to model, we take advantage of Zkreg and arithmetic circuits. But for handling the machine semantics of the aholchoracic autometer, we use a zero-knowledge subset proof. And then we use polynomial commitments to connect the two prover components. Another observation we have is very interesting about the aholchoracic autometer. We notice that for the vast majority of all the executable files in the Linux central system, if we study their XFS run, we notice that over 80%, almost 80% of them never travels 20 transitions away from the initial state. So given this locality, we could actually restrict our prover to reason about the subset of transitions that are bounded by depth 20 for almost like 80% of the files. All right, so this brings us almost like 10 times the speed up concerning the concrete performance of the provers. So in the following, I'm going to quickly go over some of the crypto constructions we designed in this work, and we're going to leave a lot of technical details especially a modified growth 16 scheme, to the paper. So our starting point is the aholchorestic automator. So we know that given a large collections of fixed strings, we can build the aholchorestic automator in strict linear time. And the nice thing is that the automata itself is deterministic. So if we do negation or complement over the automator, we still got linear cost. The first step in our scheme is to arithmetize the automata. The basic idea is very simple. We simply map each state in the automata into a number. And similarly, we could encode a transition as a 56-bit number. So these numbers are essentially elements of a big prime field. Now, we got a huge set of field elements with over 360 million elements. So apparently, we don't want to store this set on the verifier set. So we need a compact representation. A natural idea is to take advantage of Kt polynomial commitment. So for the set big T, we can encode it using a vanishing polynomial of this form, and then we generate the Kt polynomial commitment, which only costs us one curve point. Unfortunately, Kt polynomial commitment is not complete hiding, and it is also a little bit leaky. So this problem was addressed in the Zk VSQR work back in 2017. And there is a Zk VPD scheme which provides complete zero knowledge. So in this work, we further improve the Zk VPD scheme. We cut half its proof of cost, and we reduced the verifier cost from 9 pairings to only 2 pairings. And we are leaving those technical details to the paper. Another crucial construction in our paper is a zero-knowledge subset proof. So the idea is that we use arithmetic circuits to reason about the acceptance run of an input string. So there's a lot of transitions generated by this acceptance run. And we need to reason and we need to argue about that. Well, this set is actually a subset of the transition set of the automata. So of course, we need to do this using in a zero-knowledge fashion. The basic idea is to build up the scheme over the bilinear accumulator scheme. It takes advantage of the pairing equations to reason about the product relation between the polynomials. The scheme was further improved to zero knowledge by a paper appeared in CCS last year. So we further improved this scheme to complete zero knowledge, and we are able to cut a sigma product proof part from its proof so that we gain about 40% reduction in the proof size. Now, the Zk subset proof is nice, but we cannot use it directly. The reason is that there are a lot of cycles in the automata, so one transition could actually appear many, many times. So before engaging the zero-knowledge subset proof, we actually need to extract distinct elements of the transitions from a multiset. So we took advantage of an observation in the computational algebra. So if we study the formal derivative for the vanishing polynomial of these two sets, actually there's some nice product relation between these polynomials. Theoretically, it is possible to encode them using sigma particles, but we would like to take advantage of arithmetic circuits for its simplicity. So the basic idea is that we're going to feed a collection of polynomials related to all these GCDs and formal derivatives, and we feed a verifier challenge X to the circuit, and then we evaluate all these polynomials and verify that relation using the evaluation result on this random point X. So the only caveat is that this X is actually a verifier challenge. It should not be provided at the same time that these witness wires are provided. So this results in a two-stage modified growth 16 prover scheme, and we have to refer you to the details presented in the paper. But we got some very nice prover complexity result. So the entire scheme just cost us linear number of group operations, which is elegant and nice. Now, if we put all the components together, we have a trusted setup who publishes the finite state machine A, the subsets of transitions bounded by different depths, and the corresponding prover keys for polynomial commitment schemes and growth 16 systems. So we have the prover who tries to convince the verifier that behind a hash value h, this input string s belongs to this finite state automata A. So this is how the prover works. The prover first runs the secret input string over this automata A, generates the sets of the transitions, and let its maximum depth be k. So then she computes the set support, computes the corresponding commitments for the set support, and the selected subset of transitions. And then she runs two zero-knowledge subset proof, which proves that, well, this transition set is actually a subset of this tk, and this tk is a subset of the entire transition set of the automata. And because that these proofs are zero knowledge, so the verifiers learns nothing about this transition set and the selected subset. And the last step is to run the zk snark. So the prover feeds the secret input string and encryption key to the arithmetic circuit, the corresponding polynomial coefficients for the transition set and its set support, and the corresponding set support proof, which we introduced in the previous slide. So the circuit would verify that the encoding from the input string to transition set is correct. The set support proof is valid. And then it runs the encryption and hash algorithm over the input string, which generates the hash h. And then using a technique similar to the Lego snark, we are able to extract the commitment to the set support of the transition set. And notice that this is the same commitment used in the zero-knowledge subset proof. So this bridges together the two prover components. So essentially, we managed to prove that the secret string S generates the hash h, and it is indeed accepted by this public finite state machine A. So we have implemented the entire tool set over a Rust OpenMPI framework, and we run our evaluation over a cluster of 4 Google Cloud Computing C2D instances. Each has 112 virtual CPUs. So to demonstrate the performance and scalability of our tool, we used the complete hexadecimal signature set from ClamAV. We generate the malware-free proof for all the 2500 executable files in the CentOS 7. We generated about 3,000 proofs. The reason is that for some big executable files, we are chunking them into smaller pieces. So each proof is only 2 kilobytes, and it can be verified in 36 milliseconds. We further apply the inner pairing product proof to aggregate these 3,000 proof into one single proof of 2 megabytes long. And it can be verified in 6.5 seconds. So if you compare with the cost, if you have to download the CentOS and run the antivirus on the image, you probably have to spend at least half an hour for the virus scanner. But here, our zero-knowledge proof would be able to convince you that it is malware-free concerning ClamAV in only 6 seconds. The proof of cost is a little bit higher. We spend 54 hours on the Google Cloud Computing, and it costs us about $1,350. Let's look at another example. So we know that the average size of the email is about 70 kilobytes. So if we look at a typical file of 64 kilobytes, the prover time is only less than 2 minutes. So this implies that our tool is almost practical for proving emails malware-free. Interestingly, the single most expensive component in the prover time is the running time for the GCD algorithm. In the next slide, we'll show that how do we address this problem. But in summary, in this work, we have presented a very efficient solution to tackle the zero-knowledge regular language problem. Our basic approach is a hybrid prover system. Because the use of a zero-knowledge subset proof, we are able to separate the machine logic from those hash and encryption operations. So we end up with a nice complexity for the provers, that the complexity in terms of the group operations is the sum of the automata size and input string length. So we noticed that there is a recent rapid progress in the field of pre-processed lookup argument. So if the superset is pre-processed, by leveraging the lookup argument, we can further cut off the aholacratic automata size from the complexity formula, so that the prover complexity can entirely solely depend on the input string length. So we are very excited about this direction, and the implementation to further improve our tool is being planned. So this slide shows you the references that we used in this presentation, and we welcome any questions.